So my name is Zhi Li. I'm an inventor at Adeia. So this paper is based on the a recent patent we filed recently. Okay. All right. So let's jump in. So if you think photography is easy, think again. Look at those pictures. Those are the great pictures taken by professionals. So to take those pictures, you have to be very attentive, very focused, and always observing and anticipating what's going to happen next. And when the exact moment happens, you have to press a button immediately. I'm sure a lot of us are trying to do that, but it's pretty hard to do that. And once you are able to do that, you're actually missing the other part of your knife, right? You're not part of the knife anymore, you're the photographer. So what we really want is we want to achieve this. We want the camera to listen to your description. For example, I want to tell the camera, take a picture when everybody jumps. And then the camera is going to sit there and watch, analyzing the scene. And when that exact moment happens, the camera take the best snapshot. And you might be asking, why can't we just do the best mode? Well, best mode, typically it only works for a few seconds, right? And after that few seconds, you have to press the button again. And it's going to generate a lot of junk images if that's not what you want. And more importantly, a lot of interesting moments in life you cannot anticipate. You cannot say, hey, this is going to happen in the next 3 minutes, 3 seconds, so I'm going to press the best mode button right now in the hope I'm going to capture that in the next few seconds. So that's not going to work. Okay? So look at this flow. The few things should be already there. For example, you take a voice and convert the voice to text, so that should be there. But starting from the 2 steps at the bottom, observing automatically and found the best match. This is what we're going to focus on today. So a little bit background. We know that the generative AI has a lot of breakthrough recently in the last year or two. So this is a typical example of the DALL-E system. You tell the system, an astronaut riding a horse in a photorealistic style. It's going to generate something like this. Okay. Everything looks good until you think very carefully. Did I say this is a white horse? No, I didn't say that. Did I say the horse is facing that way? No, I didn't say that, right? Did I say the size of the horse? The pose of the horse? No, I didn't say anything of that. Did I say anything about the astronaut? Probably not. Okay? So that means the system is actually filling a lot of gaps which you didn't say. And this is good and bad. We're going to see why. So our initial idea is quite simple, right? If we can generate a sentence, if we can generate an image from a sentence, then immediately we can convert the description to an image. There's no problem. And then we're going to compare that with the previews from the camera and see if those 2 images match, right? If they match, then we assume we found the best match. But the problem is the image generation is kind of slow, right? You tried DALL-E and other system, Firefly. It takes like 1 or 2 minutes. But that's fine. That's just a one-time operation. The big problem is the image-to-image comparison. How do we do that? It's going to be expensive. And more importantly, this is unreliable. As I just described, for this picture, how do you know the horse is facing that way instead of the other way, right? You didn't say that. What if the horse is facing that way, but your sentence generated image is facing the opposite way? Is that still going to be a good match in terms of image-to-image comparison? Probably not. Okay, so those are the 2 problems which is blocking this idea. So let's take a step back. what is inside those generative AI model. So this is, I quote that from the original paper of CLIP. So CLIP model is actually the core of the DALL-E system. Let's focus on the left side. That's the most important part. That's the training process. The training process is actually have a huge number of pairs of image and text description so that both of them map to the same space, the same vector space. So there's a text encoder here, and then there's an image encoder here. If there's a match, then of course the vectors are going to match. So that's the core idea here. So with that in mind, we can totally get rid of the step of generating image from the text, which is the right part. So we totally don't worry about that anymore. Now the problem becomes very simple. We're going to encode the text description and the image to two vectors. Now we can just compare those two vectors. That's a very simple mathematical problem, right? You just do the cosine similarities. You project one vector to the other one and see how close they are. If we can let the camera to do that automatically, then ideally we're going to say the camera is going to start that with relatively low value of similarities, and over time, if the thing is happening exactly as I want it to happen, then the similarity is going to increase. At some point, it's going to reach the peak, and that's the exact moment I want to take the picture. But everything is going to happen on the device automatically. And you only need to tell the device what it's going to capture, and then it's going to observe there and then take the picture automatically. You don't have to interact with the device anymore. So now this is the improved idea. Instead of doing image-to-image comparison, we use the two encoders. We encode the text description to a vector, then we continuously encode the previews from the camera to a sequence of vectors. And then we just compute the cosine similarities, which is a dot product. Should be very easy, right? Then we can find the best match. And the beauty of this is it's going to be very fast. The encode of the text description is going to be one time, and the encode of the image from the preview of the camera is going to be fast too, because think about this. For the previews from the camera, we can reduce the resolution, and we can increase the frame rate. So that's going to happen very quickly. And dot production, we don't even care about that anymore. It's so fast. So I did some experiment using Google Colab, which I just use the GPU accelerator. There's a bunch of setup here. I just use one CLIP model, which is about 300 megabytes. Not the biggest one, not the smallest one. I found it's working very well. So the image pre-processing, like I said, we don't really need to analyze the full resolution image. We just downsample that to 224 by 224. And text pre-processing, we don't intend to tell a very long story to the camera, right? It's going to be a short sentence. Take a picture when everybody jumps. Take a picture when a kid falls down, something like that. And the result is very encouraging. So for each frame, it's less than 2 milliseconds. That means we can achieve 500 frames per second performance. This is a work still in progress. So next step, we're trying to distill the model to reduce its size. And we're trying to fine-tune the performance so that the model is going to work better for photography. And our final goal is to make this work on mobile devices without constantly rely on the server on the cloud side. Maybe we can make it work on microcontrollers. Let's see what will happen. So enough talking, let's have some demo. So I guess this is one of the Winter Olympiad. There are two moments I want to capture. The first is figure skater jumping high. The second is a figure skater falling to the ground. As a matter of fact, I can run these two moments in parallel, and the curve shows me the cosine similarities. So the x-axis, that's the ID number for each frame. As you can see, at some point, the similarity is going to reach the maximum, and that's exactly the moment I want to capture. So this is the frame 35. And for this example, the person matches at frame 65, and looks pretty good, technically, okay? This is another example. I want to capture the moment when a whale jumping out of water. Well, this looks totally expected. But the one thing I want to mention that here is when I tell the model a whale jumping out of water, there's something implicit I told the computer, right? What does it mean out of water? What does it mean you achieve the maximum similarity? That means the body of the whale, maximum part of the body of the whale is above the water. And the CNIF model definitely got it, okay? This is pretty straightforward. A soccer ball being kicked. So the curve is pretty clear. There's only one best moment there, and it captured it. So this is the example I brought up at the beginning. I want to capture a group of people jumping. So I say, take a picture when a group of people jump on a sunny beach. So what's going to happen is it's going to calculate the similarities, and of course, it's going to find at the frame 14, that's the best match. But pay a little attention here, the curve actually dropped a little bit here. If you look at the video, all those people, they don't just jump directly. They actually duck down a little bit and then jump. So the action of ducking down is the opposite of this sentence. That's why the similarity starts to drop. So that means this model actually works very well. It's describing the action, it's also describing the opposite action. That's a relatively straightforward example. A horse jumping over hurdles. Okay, so there's no setback, it's just keep running, and then at the top of this curve, that's the exact moment I want to capture. So this one is the challenge one. I want to capture the moment when Tiger Woods celebrate. So Tiger Woods do this, and actually he's holding this for a little while. And the CNIF model actually can differentiate that. So only at this moment, it matched the sentence exactly. And the other moment is kind of okay, but not as good as that one. So this is pretty good. All right, finally, thank everybody to follow me so far. For that reason, I want to, Simon gave you 2 thumbs up, and it captured that moment exactly. And also, I want to introduce my company again, Adeia, Igniting Innovation. If you are interested in this technology, talk to me. We can license it.
Okay, thank you very much for your presentation.
So the data doesn't have to stay persistent on device. I just need to keep a small window. When every preview image, I compute the vector, I don't need that image anymore, right? Or I keep a small window and take the high resolution image, and those are the candidates. I may be able to keep them. If they fall below to the threshold, I don't need them anymore. So that's one of the benefits compared with burst mode. Burst mode, you save everything, right? In our case, is a moving window. You only keep what's best so far. All right?